Hello again. Welcome to Basics of Finite Element Analysis, Part 2. Today is the fourth day of the second week, or fifth day of the second week. And what we are going to discuss today is a continuation of what we were talking about in the last class. And what we had started discussing is as to why energy convergence in FEA solution happens from above. So, we were developing a mathematical proof for that, and that is what we will continue to do in today's class. So, very briefly I am going to recap what we discussed in the last class. So, we had said that our so for m is equal to 1, if m is equal to 1, then our governing differential equation was a1 du over dx, excuse me, d over dx is equal to f. So, this is for the case m is equal to 1, and we had developed its variational form like this. So, it was, so I am integrating it from 0 to L. So, again 0 to L, the integral, the variational form. So, this is the governing equation, and then the variational form is a1 v prime u prime minus vf dx is equal to 0. And associated with this variational form was its quadratic functional, and this was 0 to L half a1 u prime whole square dx minus 0 to L uf dx equals I of u. So, this is the this is the integral weighted residual form of the governing equation. B is the variational form of this weighted residual form, where I have weakened the differentiability, right? And excuse me, I am sorry, here there should not be any integral sign. So, equation A is the governing differential equation. Equation B is the weighted residual form or variational form of equation A, and equation C is the associated functional, which actually also physically represents the energy in the system. So, this is for m is equal to 1, and I can generalize this by writing the following relations. So, if m is more than 1, it could be 2 or higher than that, then the general equation we had discussed and we had shown was minus 1 to the power of I di over dxi ai du or diu over dx I is equal to f. So, this is m is equal to 1 to whatever number it is on, okay, and the associated variational form, and just by extending the logic we will just write it directly. If you want to find out the mathematical details, you can work into that, but we have already developed the mathematical details for the case m equals 1. You can develop for other values of m also. So, the variational form is integral 0 to L, so here it is m is equal to 1 to m, and the I equals 1 to m. So, the variational form is half summation I equals 1 to m. So, it is AI div over dxi diu over dxi minus Vf dx is 0. This is the variational form. And the associated quadratic functional is 0 to L half, and there shouldn't be half here. So, associated quadratic functional is I equals 1 to m AI diu over dxi, the whole thing square dx minus 0 to L u f dx is equal to I u. Okay. So these are general equations, and these are for m equals 1 case. And we know that I represents, in this case, the energy, right. So, let us find out what is the difference in energy. So, I u h minus I u. So, I u represents the energy associated with the exact solution, and I u h represents the energy associated with finite element solution. U h represents finite element solution. So, I represents the functional associated with finite element solution. So, this equals 0 to L half, and for purposes of brevity I will no longer write A1, I will just write A, and this is u h prime square minus u dx plus f of u minus u h 0 to L dx. Okay. So, the negative sign has gone, this is a negative sign, but this negative sign has gone in the second term in this equation, because instead of u h minus u I have done u minus u h, that is why. Now, we know that f equals minus d by dx a du over dx. Okay. So, with that understanding I will write this equation again, 0 to L half a u h prime square minus u prime square and then minus, and I am going to replace f by this expression. So, it is minus d by dx a u prime and u minus u h, and this entire thing is going to be integrated with respect to x. Now, we know that if I have a function g prime, so if I have a function g and I have a function h, then integration of g prime h between the limits 0 to L is nothing but integration negative of g h prime dx plus g h 0 to L. This we have seen several times in this class. So, this is like G prime and this is like H. Okay. So, I can do integration of this thing by parts. So, I get half A u h prime square minus u prime square, and then instead of this entire expression I get a plus term because it is minus g h prime, and I get a u prime, and then it is u prime minus u h prime, and this entire thing is integrated with respect to x, and then plus I get g h. So, I get some other terms. So, what is g h? It is a u prime u minus u h 0 to L. Okay. Now, we had said, okay, so this is a bar problem, and let us say that I am defining this bar problem is such that the value of u at x is equal to 0 and x is equal to L is 0. I want to basically drop these boundary terms. Okay. So, if it is 0, then this term goes away. If the boundary terms are 0, this term goes away. So, what we are left with is half 0 to L a u h prime square minus a, no, actually I am going to remove this a by 2. So, minus a u prime square plus a u prime square minus a u prime u h prime dx. Okay. So, this term and this term when I add, I am left with 0 to L a by 2 u h prime square minus 2a u prime u h prime plus u prime square dx. Okay. So, this is equal to 0 to L a by 2 u h minus u prime square dx. Now, a is more than 0. We assume it because a, what is a in context of the bar thing? It is E times cross sectional area. E is positive, cross sectional area is positive. So, a is always positive, and this will always be this entire thing, not the thing inside the bracket. This will always be positive because even if the term inside the bracket is negative, it is raised to the power of 2. So, it will always be positive. Right. So, the entire, so what that means is that right hand side of this equation is always more than 0, or it could be 0 also. If the term in the bracket is 0, then it could be 0. If the solution is exact, then it will be 0. If the solution is inexact, then it will be more than 0. It will not be negative. That is the point I am trying to make. Okay. And what is the left side? The left side of the equation is I UH minus I U. So, I say that I UH minus I U, this is the left side, and the right side is always more than 0. So, this is always more than or equal to 0. When the solution is exact, then it will be 0. When the solution is inexact, then the finite element solution for energy, here we are doing this thing for energy. For energy, it will always be more than 0. So, the energy of the system as computed through finite element analysis will always be larger than the actual energy, okay, which means that if I am going to plot, suppose I am increasing the H size, H is represents size of element, okay, the actual energy, it could be this is actual energy level. And the finite element energy will converge from top. This is I U H. It will never converge from the bottom. It will never converge from the bottom side. So, so what we have shown in today's lecture is that energy convergence in finite element solutions always happens from the top, okay. If you are getting a solution, at least for simple non-linear, for linear conservative systems, where energy is coming from the downside, then you should think either your model is not right or something is wrong, because theoretically energy should always converge from the top side, okay. So, with this discussion, we will close our today's discussion, and tomorrow we will extend this discussion a little bit more, and we will see that how all this relates to different types of solution variables, and how can we make use of this very important observation in context of whenever we are doing finite element analysis, then how can we make use of this important observation. So, thanks a lot, and we will continue this discussion tomorrow. Thank you.